Hello, I'm Mr. Charlie and welcome back to AP Physics Review. This is lesson 3, two-dimensional motion. If you recall last lesson we talked about motion along a one-dimensional line or curve. For example, a car driving along a road, or a train moving along railroad tracks, or a person running in a straight line. But notice these are not super realistic conditions, right? Usually people and cars turn and generally move in planes or three-dimensional spaces rather than simple one-dimensional lines. However, the one-dimensional motion is still a very valuable example to study because every example of higher dimensional motion, both 2 and 3D, can be broken down into simple one-dimensional problems. Using the way vectors break down into their horizontal and vertical components, we can then break down any more complicated motion in 2 or 3 dimensions into 2 or 3 simple one-dimensional problems. So although I won't do an explicit lesson on 3-dimensional motion, all of the techniques we discuss today will also be applicable to 3D. Whereas if you resolve the horizontal and vertical components to do 2D problems, for 3D all you do is resolve the x, y, and z components into their fundamental components and then solve the simple 3-dimensional problems. So basically, 3 simple one-dimensional problems. So basically your approach for any 2 or 3D problem will be to break up the complicated motion into the motion along the axes and then solve each axis as a one-dimensional problem as we did last chapter. So let's get started. As I said, we know how to deal with velocity and acceleration of an object if it's confined to a line. But what if it's not? What if it's confined to a plane instead? Well, then we have two-dimensional motion. One common example of two-dimensional motion is a trajectory of, say, a cannonball. So if you have this cannonball here, it's fired, it moves up and then down in a parabola. And this is, okay. And now notice this is very similar to what we saw last lesson where we graphed the height of a ball as a function of time, and we threw it up and then it came back down. But notice the difference. In physical space, this is called phase space. In physical space, it moved straight up and then straight back down. There was no horizontal displacement. So this was height over time. This is different because in this case we actually have physical displacement. This is height, or y, versus displacement actually of both vertical and horizontal displacement. If you wanted to graph the time, you would have the displacement over time, you would have 2 graphs. This would break up into an xt graph and a yt graph. This being the height, and this being the time, and this being the horizontal distance, this being the time. And now the y graph would act as you expect, the same thing, same parabola, goes up and down. But the horizontal part would be constant velocity, right? There are no forces acting in the x direction, so it moves at a constant velocity, and we learned last time the slope of an xt graph gives the velocity. So this would be the xt graph. So again, this is a distinct case where this is actually the trajectory of the line. It's the physical path that it follows. And we're going to talk about how to analyze that. So we basically already know how to do this. We have all the tools we need. All we need to do is use our vector arithmetic and our knowledge of 1D motion. So for example, consider the definition of vector subtraction from last lesson. If we have some y here and some x here, then we have 2 vectors, 2 location vectors, locating point A and locating point B, and this is B minus A. Okay. So notice, let's look at